The paper introduces the concept of dipole-obstructed Cooper pairing in superconductors, leading to topologically enforced nodal structures. It begins by presenting a Chern-vorticity theorem that guides the identification of specific Fermi surfaces, FSs, where all intra-Fs Cooper pairings are obstructed due to a quantized dipole pattern in the Berry curvature. This obstruction results in the formation of zero-energy Weyl nodes and/or nodal loops in the Bogoliubov-de BDG spectrum. The authors apply this concept to half-Heusler superconductors, such as YPTBI and LUPDBI, which are believed to exhibit mixed parity singlet septet pairing. They find that the dipole obstruction naturally exists in the septet pairing channel, contributing to the observed BDG line nodes in experiments. The paper also provides a detailed derivation of the Chern-vorticity theorem, which is essential for understanding the relationship between the net vorticity on a manifold M1 and the single particle Chern numbers of the involved block states. This theorem serves as a foundation for identifying topologically obstructed pairings and predicting the resulting nodal structures in superconductors. Overall, the research introduces a new mechanism for understanding nodal superconductivity, particularly in systems with complex Fermi surfaces. The findings have implications for the study of unconventional superconductivity and the design of new materials with desired nodal structures. The Chern-vorticity theorem generalizes the obstructed nodal pairing in superconductors to encompass inter-Fermi-surface pairings. This theorem is based on the quantization of the Berry dipole, a quantized dipolar texture of Berry curvature, and the enforcement of a mirror symmetry along the dipole axis. A minimal model with Berry dipole physics is introduced, featuring a 3D minimal Weyl semimetal and a nodal loop semimetal under different conditions. The model Hamiltonian is given by H0 equals 2 kz, kx sigma x plus ky sigma y, plus kx squared plus ky squared kz squared plus sigma z, where sigma determines the phase of the system. The Fermi surface topology is found to be sensitive to the value of sigma. For micro greater than sigma, a single spherical-like Fermi surface is present, while for micro less than sigma, a pair of closed spherical Fermi surfaces or a single torus-like Fermi surface emerges, depending on the value of sigma. These Fermi surfaces are either closed or effectively closed, guaranteeing a quantized Berry dipole. The research then explores Cooper pairing physics on the Berry dipole Fermi surface by updating the Hamiltonian to a Bogoliubov-de Hamiltonian. H k equals H0 k micro increment k H0 k micro, where increment k is the pairing matrix. The pairing matrix is expanded up to O k squared, and all pairing channels are classified based on the irreducible representations of the C4H group. The analysis reveals that a general pairing with I phi equals 0 must be topologically obstructed for micro greater than sigma, which applies to all sigma x, y pairings. However, the sigma plus or minus components of increment k can contribute to I phi through the winding phase of d plus or minus k around the equator for micro greater than 0. Micro less than 0, provided d plus or minus kz equals 0, does not equal 0. This underscores the significance of the Chern-vorticity theorem in understanding the topological obstruction of Cooper pairings in superconductors with inter-Fermi surface pairings. The Berry dipole Fermi surface exhibits obstructed and nodal pairing channels, as demonstrated by the analysis of the pairing classification following the C4 irreducible representations. Only the O and BU pairings can contribute to the intrinsic phase winding I phi, resulting in a non-zero odd integer-valued vorticity nu for all relevant pairings. This leads to the conclusion that all intra-Fs pairing channels for the Berry dipole Fs are obstructed and nodal. The dipole-induced obstruction is explicitly illustrated by considering the pairing channel increment equals dx, k, sigma x, where dx, k, is an odd function of k plus or minus equals kx plus or minus iky. The corresponding phase winding of d plus or minus around the equator must be 4 meters plus 1 pi with m element of z, resulting in a non-zero odd integer valued nu. A concrete example is considered, where the Fermi surface is parameterized by a polar angle theta and an azimuthal angle phi. The wave function xi, k is found to be singular at the North Pole, implying an obstruction to define a globally smooth gauge. A different gauge choice is considered for theta element of 0, pi, 4, union, 3 pi, 4, pi, to ensure the wave function is merely locally singular. The effective pairing gap increment f is calculated, featuring two zeros on m+, one at the North Pole and another at the equator. The vorticity of the North Pole 0 is found to be nu0 equals 1, while the vorticity for the equator 0 is also 1. The net vorticity nu is found to be 2 for m+, consistent with the prediction of the Chern-vorticity theorem. The vorticity-induced pairing zeros are found to always exist, regardless of the detailed form of dx, k. The zeros of dx, k, itself may lead to additional zeros of increment f, beyond the topologically obstructed ones. The counting of nu for intra-Fs pairing is found to depend on a special gauge choice with which m plus or minus are effectively closed. The MZ symmetry guarantees the existence of such a gauge, ensuring the nu counting is always possible. The nodal structure of increment f is found to be gauge invariant, and the Chern-vorticity theorem is applied under a proper gauge to thoroughly inform the obstructed pairing zeros that are gauge independent. The 2 EU pairing dx, k, equals k plus is taken as an example to numerically explore the nodal nature of the obstructed SC phases. The pairing gap function is plotted on the corresponding Fs, and its evolution is tracked as a function of sigma and micro. The BDG Weyl nodes and nodal loops are highlighted in black, and the results are found to be consistent with the analysis of vorticity counting. The application to J equals 3/2 SCs, such as YPTBI and LUPDBI, demonstrates that the BDG line nodes are deeply rooted in the mechanism of dipole obstruction. A generalized Luttinger cone Hamiltonian is used as a normal state of interest, and the results are found to be consistent with the expected behavior of the barydipole Fs. The isotropic Luttinger semimetal model encapsulates the low-energy normal state of general J equals 3/2 half-Heusler superconductors, featuring mixed parity singlet septet pairing. Intraspin pairings are dipole-obstructed, carrying a non-trivial pairing vorticity of 1. This leads to the emergence of pairing zeros on both the north and south poles of the Fermi surface, Fs. In the isotropic limit, alpha equals 1, these dipole-obstructed pairing zeros persist, resulting in 6 p-wave-induced point nodes for J equals 3/2 superconductors. However, when a subdominant swave pairing is introduced, the spin degeneracy of Fs's is lifted, causing accidental inter-Fs band crossings that manifest as line nodes. Notably, the dipole-obstructed pairing nodes appear at a finite energy, ensuring the presence of BDG line nodes even with an arbitrarily small swave pairing. A small asymmetric spin-orbit coupling term intrinsic to zinc-blende materials, omitted in this discussion, mixes S and P wave pairings and affects the BDG band spectrum similarly to swave pairing. For a detailed examination of the ASOC term, refer to the supplementary material. In half-Heusler superconductors, topological semimetals with a J equals 3/2 spin-orbit coupling, dipole obstruction plays a crucial role in shaping the nodal structures of the Bogoliubov-de spectrum. To elucidate this phenomenon, the authors propose a Chern-vorticity theorem, which establishes a link between the topological vorticity of a superconducting order parameter and its Chern number. This theorem provides valuable insights into the interplay between topological properties and the emergence of nodal structures. The research focuses on the singlet septet pairing channel, where dipole obstruction significantly contributes to the observed nodal structures in experimental findings. This work highlights the profound impact of delicate topological bands on correlated electronic orders in real-world quantum materials. The authors also explore the potential for extending the concept of dipole obstruction to other non-superconducting Luttinger semimetals, such as mercury-2 telluride and Pr2Ir207. Furthermore, they identify unobstructed pairing zeros, resulting from geometric textures of the block states on the Fermi surfaces, as an area worthy of future investigation. The implications of these findings are far-reaching, shedding light on unconventional superconductivity in systems such as twisted bilayer graphene, Weyl semimetals, and Dipole superconductors. The importance of considering spin-orbit coupling and crystalline symmetry in determining the properties of these exotic superconductors is underscored. Recent studies on Weyl semimetals, anomalous Hall ferromagnetism, and topological superconductivity are comprehensively reviewed. The literature highlights the investigation of Weyl semimetal properties, including wave states, anomalous Hall ferromagnetism, and topological superconductivity. Conversion rules for Weyl points and nodal lines in topological media are explored, along with the concept of massless multifold Hopf semimetals. Dipole semimetals and dipolar Weyl semimetals are discussed, showcasing their unique properties. Topological superconducting vortices, the delicate topology of Luttinger semimetals, and Majorana surface modes of nodal topological pairings in spin 3/2 semimetals are also examined. Research on unconventional superconductivity in Luttinger semimetals, singlet-quintet mixing in spin-orbit coupled superconductors, and pairing states of spin 3/2 fermions is referenced. The Z2 spin-Hopf insulator, helical hinge states, and the returning Thouless pump are further discussed. The literature review concludes with references to a classic study on the band structure of HGTE and a more recent study on the quadratic Fermi node in a 3D strongly correlated semimetal. This comprehensive review sets the stage for the author's own contributions to the field, providing a thorough understanding of the current state of research in Weyl semimetals, topological superconductivity, and related topics. In the supplemental material for Dipole-Obstructed Cooper pairing, Theory and Application to J=3/2 superconductors, Penghao Zhu and Rui-Xing Zhang delve into the intricacies of their research. The document is structured into 7 sections, each addressing a different aspect of the study. Section S1 provides a detailed proof of the Chern-vorticity theorem, which involves constructing a vector S that is invariant under U(1) gauge transformations. This vector plays a crucial role in understanding the relationship between the Chern number and the Berry connection, with implications for the smoothness of gauge patches over the manifold. Section S2 explores mirror symmetry and quantized Berry-Dipole flux in 2-band tight-binding models. This section delves into the specifics of how these models behave under certain symmetries and their implications for the quantization of the Berry-Dipole flux. Section S3 focuses on Cooper pairings of the Berry-Dipole Fermi surface. Subsections A and B concentrate on the projection of intersector pairings onto the Fermi surface and the symmetry analysis, respectively. This section highlights the importance of considering both the normal and anomalous Green's functions in the context of the BCS theory. Section S4 examines the annihilation of nodal points upon varying the Fermi level in normal Weyl semimetals. This section demonstrates how the nodal points can be eliminated by adjusting the Fermi level, leading to a fully gapped superconducting state. Section S5 discusses the projection of intersector pairings onto the Fermi surface and symmetry analysis. Subsections A and B detail the projection process and the symmetry properties of the projected pairings, emphasizing the role of the Berry-Dipole moment in determining the robustness of nodal points. Section S6 addresses perturbations from asymmetric spin-orbit coupling, an essential consideration in real materials where perfect symmetry is not always achieved. This section shows how such perturbations can lead to the formation of nodal rings rather than points. Finally, Section S7 discusses the Berry-Dipole superconductor, a novel type of superconductor proposed by the authors. This section outlines the key features of this new class of superconductors and their potential implications for future research. The supplemental material concludes with a list of across the boundary of 2 patches, denoted by L0 in Fig. S1, A, singularities of A1, K1, and A2, K2, arise, satisfying the equations lim delta right pointing arrow 0 integral, L0 plus delta, L0 delta, A1, K1, dk1 equals 2 pi C1, lim delta right pointing arrow 0 integral, G, L0 plus delta, plus T, G, L0 delta, plus T, A2, K2, dk2 equals 2 pi, det G, C2. The determinant of the transformation G, denoted by det G, appears in the second equation due to the definition of C1 and C2 over M1 and M2 under the same orientation choice. For instance, in the case of a 2D closed surface in 3D, the normal vectors of M1 and M2 are chosen to point outward from their enclosed region. If G is an improper transformation, such as inversion, det G equals 1, and the path integral corresponds to the Chern number defined with respect to normal vectors pointing inward the enclosed region, as illustrated in Fig. S1, B, opposite to C2. The Berry connection is gauge-dependent, whereas S is gauge-invariant and continuous across the gauge patch boundary, implying that lim delta right pointing arrow 0 integral, L0 plus delta, L0 delta, SDK1 equals 0. Consequently, partial differential K1 phi, K1, must have its own singularities, or vortices, to cancel or balance those from the Berry connection, leading to the equation lim delta right pointing arrow 0 integral, L0 plus delta, L0 delta, partial differential K1 phi dk1 equals lim delta right pointing arrow 0 integral, L0 plus delta, L0 delta, A1, K1, GTA2, K2, dk1 equals 2 pi, C1, det G, C2. The net vorticity of O, K1, denoted by nu, can be calculated as nu equals n Airy summation vortex integral partial differential K1 phi dk1, as illustrated in Fig. S1a. The Chern-vorticity theorem, a crucial component in the study of Berry-Dipole-Fermi surfaces, is derived by rewriting the expression for nu through line integrals over L0 plus or minus delta and B1, 2, resulting in equation S6. In superconducting SC systems, the Chern number C2 is defined as the limit of the integral of the Berry connection A2, K2, over the Fermi surface, Fs, patches. A2, K2, is computed using the wave function xi, e, star operator 2, K2, and its opposite sign is observed when compared to the Chern number of electronic block states, xi, e, 2, K2. The concept of mirror symmetry is introduced, which can quantize Berry-Dipole flux over the Fs for general two-band tight binding models. This is achieved by considering a two-band Hamiltonian H, K, that respects a z-directional mirror symmetry Mz. The mirror symmetry requires the Hamiltonian to be diagonal at Kz equals 0, resulting in the 1D equator M0 being topologically equivalent to a 0D point. Consequently, the Fs patches M plus or minus are effectively closed 2D manifolds, over which the Berry flux must be quantized. The general pairing matrix for a Berry-Dipole system is given by equation S7, where dx, k, and di, k, are odd and even in k, respectively. The Fermi statistics require the pairing matrix to be odd under k right pointing arrow k. The effective pairing matrices increment f, I and increment f, 2 are derived in the two gauge patches, as shown in equation S8. These expressions summarize the consequences of each pairing channel in the Berry-Dipole-Fermi surface. This discussion connects to previous pages by building upon the concepts of Berry-Dipole-Fermi surfaces and Chern numbers. The novel idea presented is the quantization of Berry-Dipole flux over the Fs for general two-band tight binding models, which is a significant finding in the field. However, the limitations of this approach are acknowledged, as it may not apply to n-band models with n greater than 2, which may require additional symmetry protection. Future work may involve exploring these limitations and generalizing the results to more complex systems. In the context of superconductivity, the pairing zeros of the gap function increment, k, are analyzed in terms of vorticity nu. The authors focus on dx, di, and d plus or minus channels, where dx exhibits zeros at theta equals 0, pi, 2, pi, and d plus or minus channels uniformly vanish when projected onto the Fermi surface. A general increment, k, consisting of non-zero dx and d plus or minus components is also considered, leading to pairing zeros at arbitrary positions. For instance, the case of dx equals kz and d plus or minus equals k minus or plus, where k plus or minus equals kx plus or minus iky. results in zeros at theta equals 0, pi, 4, 3 pi, 4, pi. The boundary term in EQ2 is determined by the phase winding of d over the equator, contributing +1 to nu according to EQ. S6, with C1, det G, C2 equals 2 for micro less than 0. The net vorticity in this case is 1. A symmetry analysis is performed, discussing the constraints imposed on pairings by the C4H point symmetry group. The authors examine the character table for C4H and define an irreducible representation, irrep, or symmetric channel of C4H as a pairing increment, K, that satisfies EQ. S10. Different irreps correspond to different representations of symmetry operators for the BDG Hamiltonian, as shown in EQ. S11. Focusing on irreps O, BU, 1 EU, 2 EU, the authors find that dx plus or minus must vanish at the poles of the Fermi surface, which are C4 fixed points, if beta x plus or minus does not equal 1. Additionally, dx plus or minus are even in kx, ky, and must be odd in kz if beta x plus or minus equals plus or minus 1. Consequently, dx plus or minus vanish at the equator where kz equals 0. For micro greater than sigma, the normal states are identically 1, 0, t, 0, 1, t, for micro greater than 0, micro less than 0, over the equator of the Fermi surface at kz equals 0 plane. Therefore, increment f equals d plus d, for micro greater than 0, micro less than 0. The authors conclude that the irreps 1, 2 EU with vanishing d plus or minus correspond to a zero boundary term in EQ. 2. Of the main text. However, the irrep O, BU, can have non-zero d plus or minus with beta plus or minus equals minus or plus I, plus or minus I. In the context of topological obstruction, superconductivity is analyzed for the case where the chemical potential, micro, is less than the superconducting gap, sigma, with sigma being negative. This scenario is characterized by a torus-shaped Fermi surface for the normal liquid state, featuring two boundaries in each of the M+ and M regions. Contrary to the Chern-vorticity theorem, which assumes a spherical Fermi surface, the net vorticity can be zero, allowing for non-nodal pairings. This is demonstrated through the character table for the C4H point group, as shown in Table I. The BDG Hamiltonian, which describes the behavior of superconductors in the presence of a magnetic field, is also explained in detail. For a specific pairing channel, such as Kz sigma x plus K sigma plus K plus sigma, the system exhibits a fully gapped superconducting state, as depicted in Figure S2. Furthermore, the annihilation of nodal points upon varying the Fermi level in normal Weyl semimetals is explored. A minimal, inversion symmetric model for a Weyl semimetal is presented, along with its corresponding BDG Hamiltonian. Unlike the nodaloop conversion observed in the main text, the two nodal points merge and annihilate each other as the chemical potential decreases, micro less than 0, as illustrated in Figure S3. This comprehensive analysis of topological obstruction in superconductivity highlights the possibility of non-nodal pairings in certain scenarios and discusses the annihilation of nodal points in Weyl semimetals. In Dirac dipole semimetals, comprising two copies of Berry-Dipole semimetals with opposite orbital sectors, the analysis of nodal behaviors in intersector pairings is crucial. Focusing on the case where sigma equals 0 and micro less than 0, the authors simplify the analysis by describing the pairing matrix as a 4x4 matrix, consisting of intra- and intersector components. The nodal structures of the intrasector pairing, increment intra, mirror those found in Berry-Dipole semimetals, while the intersector pairing, increment inter, is the primary focus. The general form of increment inter includes terms involving Pauli matrices for spin and orbital degrees of freedom. To project the intersector pairing onto the Fermi surface, Fs, the authors employ specific gauge patches for the eigenstate wave functions of the Hamiltonian HDD. This projection yields the effective intersector pairing, increment inter_f, in two distinct gauge patches. The results reveal that increment inter_f exhibits a complex structure, comprising various combinations of Pauli matrices and spatial derivatives of the gap functions. Figure S3 illustrates the superconducting gap over the Fs for HWSM, K, with M equals 0.1 and different chemical potentials μ. This figure demonstrates how decreasing μ leads to the annihilation of BDG Weyl nodes, resulting in a full energy gap. This analysis provides a comprehensive understanding of the nodal behaviors in intersector pairings within Dirac dipole semimetals, highlighting the intricate interplay between different components of the pairing matrix and their projection onto the Fermi surface. In Dirac semimetal systems, the analysis of nodal structures and symmetry constraints on pairing channels is crucial. The authors focus on geometry-obstructed nodal pairing, which is determined by normal state wave functions and independent of the D, J matrix details. Various nodal structures are identified for different pairing channels, including dx, 0, di, 0, dx, z, di, z, dx, x, di, x, dx, y, and di, y, each with its own set of constraints imposed by spatial inversion symmetry and time reversal symmetry. The authors examine the symmetry constraints for dx, y, x, y in different ERIPs of the C4H times T group, considering both even and odd parity states. This analysis reveals that certain pairing channels are ruled out due to Fermi statistics or spatial inversion symmetry, while others are enforced to be purely imaginary or real by time reversal symmetry. Different ERIPs of the TD group, such as A1, are associated with specific pairing channels like SWAVE and P-wave pairings. The paper also explores the effect of asymmetric spin-orbit coupling, ASOC, on dipole-obstructed nodal points, introducing a linear Dresselhaus term as a perturbation. This term adds complexity to the analysis, highlighting the importance of considering real material properties in understanding Dirac semimetals. The interplay between nodal structures, symmetry constraints, and pairing channels is crucial in understanding the behavior of Dirac semimetals. The author's analysis provides valuable insights into the role of spatial inversion symmetry, time reversal symmetry, and ASOC in shaping the pairing channels and nodal structures in these systems. The authors delve into the effects of spin-orbit coupling, SOC, on dipole-obstructed intrasector pairing in a Dirac dipole semimetal with P-wave pairing and a Luttinger semimetal with both SWAVE and P-wave pairings. In Figure S4, AB, the superconducting gap over the Fermi surface, Fs, for these two systems is depicted, while Figure S4, CD, illustrates the energy spectra along the green arrow paths, highlighting the degeneracy rooted in the dipole-obstructed intrasector pairing. The rotation generators Jx, y, z for j equals 3/2 are defined, which are essential for understanding the nodal structures of projected pairings. The SOC term is added to the Luttinger cone model, and its effect on the dipole-obstructed intrasector pairing is examined. For the Dirac dipole semimetal with P-wave pairing, the nodal points due to the dipole-obstructed intra-Fs pairing at two poles are deformed into nodal loops, similar to the effect of the SWAVE pairing term. A novel case is discussed where the dipole-obstructed Bogoliubogda genase, BDG, nodal points themselves carry a barydipole charge, referred to as a barydipole superconductor. The BDG Hamiltonian with sigma equals 0.1 and increment, k, equals kz sigma x is considered, where the normal states exhibit Weyl points. Focusing on nodal points 2 and 3, numerical calculations of Barry phases along the azimuthal direction over green and gray Gaussian surfaces reveal that these points are BDG Weyl nodes carrying a barydipole charge. The barydipole charge constrains pair annihilation, leading to the formation of a nodal loop in the kz equals 0 plane instead of being gapped out. This occurs because increment, k, equals 0 at kz equals 0. Making all eigenstates of the BDG Hamiltonian identical on the kz equals 0 plane and thus over the equator of the Gaussian surface surrounding both nodes. The concept of a barydipole superconductor, a novel topological superconducting phase, is explored in this paper. This phase exhibits nodal points with non-zero Barry curvature and can be realized in certain half-Heusler compounds, such as YPTBI, under pressure or doping conditions that achieve an inverted band structure. The authors employ the Green's function approach to calculate the Berry phase for these systems, demonstrating quantized fluxes at the nodal points. An analysis of the stability of these nodal points against perturbations reveals their robustness against certain types of disorder. The implications of this new phase for understanding unconventional superconductivity in spin 3/2 topological semimetals are also explored. Exotic pairing states, including singlet-septet pairing, are highlighted as potential outcomes, with suggestions that tuning the parity mixing of these pairings could lead to novel superconducting behaviors. This work introduces a new paradigm for topological superconductivity, leveraging the interplay between band inversion and spin-orbit coupling to create nodal points with non-zero Berry curvature. The findings have significant implications for our understanding of unconventional superconductivity and may pave the way for further research into symmetry-protected crystalline superconductors and other exotic phenomena in topological materials.